This is part 8 in our series of lectures on other forms of induction. In this lecture, I'm going to show you an interesting application of the well-ordering property. I'm going to use it to prove that the square root of 2 is irrational. So first of all, recall that the well-ordering property says that every non-empty subset of the natural numbers has a smallest element. It seems like such a trivial statement and so obvious that you wouldn't think you could deduce anything of any consequence from it, but I think it's not that easy to see why the square root of 2 is irrational, and so I think it's impressive that we can deduce it just simply from the well-ordering property. Here's a statement of what we're going to do. We're going to prove the following theorem using the well-ordering property of the natural numbers. The theorem says that the real number root 2 is irrational. Here's the proof of the theorem, and I think it's a really nice proof. It's not the one that's traditionally given to prove that root 2 is irrational. It's a nice argument, and I think it's something that you should all learn to do. For one thing, you can modify the proof to show that other numbers are irrational as well. So the proof is by contradiction. We argue by contradiction. Suppose that it's rational. So that means there exist natural numbers a and b, such that root 2 can be written as a over b. Now the key is to look at this set here. It's the set of all natural numbers such that when you multiply by root 2, you get a natural number out of it. This is a typo here. This should be the set of natural numbers. Now, we've assumed that root 2 can be written as a over b, so that means if we multiply b by root 2, we get a out of it, which is a natural number. So that proves that b is an element of this set T, and so in particular T is non-empty. So now we can apply the well-ordering property of the natural numbers to the set T. Because we have a non-empty set of natural numbers, the well-ordering property of the natural numbers says that T must have a smallest element, and we're going to denote that smallest element by n0. Okay, so what do we know about n0? We know that n0 is an element of T, so that means when you multiply root 2 by n0, it's a natural number. And we also know that it's the smallest element of T. So if n is any natural number with the property that when you multiply by root 2, it's a natural number, then n0 must be smaller than or equal to that. Well, we're going to get a contradiction by constructing an element of T which is actually smaller than n0. And here's the one that's going to work. Let's let n be the number root 2 n0 minus n0. By assumption, root 2 n0 is a natural number. We're subtracting off another natural number, so that's the difference is certainly an integer, but since root 2 is bigger than 1, that implies that this is positive integer. So in other words, n must necessarily be a natural number. I also claim that this n is strictly smaller than n0. So I'm claiming it here, and look what it would take in order to prove that this number n is smaller than n0. If you bring that n0 to the other side, it says that root 2 n0 is smaller than 2 n0, and that's true provided you know that root 2 is smaller than 2, which we certainly do know. So we start here by saying also, since root 2 is smaller than 2, it follows that this number is smaller than n0. Okay, so at this point we've established this special number n, we've established that it's a natural number, and we've established that it's smaller than n0. If we can prove that it's an element of this set T, then we'll be finished. We will have our contradiction. So what must I do to show that it lies in T? I have to show that if I multiply it by root 2, I get a natural number. So what do we get if we multiply root 2 by this n? Well, root 2 times root 2 is 2. I get 2n0 minus root 2 times n0. So once again, this is a natural number. Root 2 n0 has been assumed to be a natural number since n0 is in the set T. So the difference of these two is an integer, but since 2 is bigger than root 2, it's a positive integer, and therefore this really is a natural number. So we've shown root 2 times this number n is a natural number. And so now we have everything. That means that n lies in the set T. It's an element of set T which is strictly smaller than n0, supposedly the smallest element of T. That's a contradiction. And therefore, our assumption that root 2 is rational must be incorrect, and so root 2 must be irrational. That completes the proof. So I'd like you to try to master that proof, to try to understand it, to be able to actually write it out on your own. And in order to practice, why don't you try this exercise here? I want you to modify the proof to show that the square root of 11 is irrational. The exact details that I've shown you up here won't quite work. The proof will break down in some places. You'll have to modify it. So it's worthwhile understanding the proof for root 2 so that you can make the necessary changes in order to prove that root 11 is irrational. So give that one a try.